Well, hey, everybody. So, the goal of this next unit is just to get a little bit more practice seeing the relationship between our exponential functions and our log functions and to get a better sense of how logarithms work. Because the more you work with them, the more confident you're going to be, the better everything is going to go. So, in this first discussion, we're going to look at an example from your text. That's why it's got this text number. So, from unit 5.2.2, it's up toward the top, 5-63, if you want to look at it there. Because sometimes when I copy the words over, I know they're very hard to see. So you can find that in your text at any point as well. Okay, so first off, given this, so there's a table of x values, and then there are a few y values filled in. And from that, we are supposed to determine a relationship between the x and the g of x. Now, you folks being bright people probably realize it's going to have something to do with exponentials or logs, or else why would it be here? So let's just take a quick look at what we have going on here. So we got this one filled out already, this one, and this one. So if an 8 goes in, a 3 comes out. If a 1/2 goes in, a -1 comes out. If a 64 goes in, a 6 comes out. So I'm going to get you started, and then I want you to think a little bit. So g of x, excuse me, is in fact going to be a logarithm. I want you to see if you can figure out what the base is supposed to be. So what number here is being used as the base of this logarithm? Do a quick pause. Discuss with a classmate if you want. Unpause when you're ready to check. So the question we're asking is, okay, logarithms give me exponents. So what number to the third power gives us 8? What number to the negative first power gives us a half? What number to the sixth power gives us 64? With a little bit of guess and check, I hope you're going to come up with 2. This is a log base 2. So part B, your textbook likes to call logarithms the ancient puzzle. Okay, well, there you go. So it says, look back at the ancient puzzle, use to write an equation for g of x. Okay, well, we've done that already. So g of x is the log base 2 of x. Now, that's not the only way that you could write this, right? You could write that if I take 2 to the power of g of x, that then gives me the x value I started with. So here in red and here in blue, these express the same relationship. The one in red is just in a more traditional function notation format, but both of those would be okay there. Now, what I would like us to do is take a moment and sincerely, folks, do a pause here and check in with some neighbors. There are a few others that I want you to try and figure out for yourself. This one, 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 and this one. Those are all, I would say, easier to figure out because they come out fairly nicely. So quick pause. See if you can fill in the y values here for those locations, and then do an unpause when you're ready to check in. So we're looking just at powers of 2, right? So with a calculator or just by doing some multiplication by hand, we can get a couple easy ones here. So let's do 2 to the first power is 2. All right, so that means that here, the exponent that I put on 2 to get 2 is just 1. 2 to the second power, 2 times 2 is 4. Is that in the, okay, here. So what exponent do you put on 2 to get 4? That exponent is 2. And remember, that's what the log gives us, is the exponent you use to get that original value. Let's keep going. 2 to the third is 8, but 8 doesn't show up in this list. 2 to the fourth would be 16. Okay, so here, the exponent you would use is 4. 2 to the fifth times 2 again is 32. And that's in the list here. So the exponent would be 5 in that case. And there are no other, let me get the lights back on. We saved a little too much energy on that one. Okay. Moving on. The other numbers that I have highlighted are all smaller than 2. So we're going to need to go in the other direction here. So 2 to the power of 0, that's going to be 1, because any number to the 0 power is 1. So what exponent do you put on 2 to get 1? An exponent of 0. Now for these others. So 25.25, that's the same as the fraction 1/4. So here's where we're going to use our negative exponents. If 2 to the second is 4, then 2 to the negative second is 1/4. The negative exponent just flips that 4 to the bottom of a fraction. The same is true here of the 1/8. So if 2 to the third is 8, then 2 to the negative third is going to reciprocate that and get us that fraction. Now this last one, depending how much Math 2 you remember, integrated Math 2, it's important that you know that a root is the same as an exponent that is a fraction. So just a couple of examples. If you do 3 to the 1/4 power, that's the fourth root of 3. The denominator here is the index of your root. So if I've got a square root of 2, that means there's really an imaginary index of 2 up there. A square root is a second root. So the exponent would have to be 1/2. So 1/2. It's a little tricky. Okay, so we've filled out most of this table, which is tight and fly. Now, as far as this next question, so 0 and -1, it says, why is it difficult to think of an output of 0 or -1? For that, let's take a little look at Desmos here. And we're going to look at all the powers of 2. So 2 to the power of x. This is an exponential growth graph. And what we're seeing here is, so like when x is 1, 2 to the first is 2. When x is 2, 2 to the second is 4. When x is -1, you get there. It's 0.5. Because 2 to the negative first is just 1/2. What I need you to notice, and this is an incredibly important property of exponents, a positive number to any power, whether it's a positive, a negative, a fraction, a decimal, doesn't matter, is never going to go below 0. Can't happen, won't happen, doesn't happen. This graph is going to go down and get very, very close to 0, but it doesn't ever actually get there. So not only does the graph not ever get to 0, so here there is no exponent you can put. I'm just going to put here, it doesn't happen, not or even better yet, I'm going to put undefined. There is no exponent you can put on a 2 to get 0. And similarly, there is no exponent you can put on a 2 to get a -1. We saw that graph. It doesn't ever go down into the negatives. So that's the reason it's difficult to find such an output. They simply don't exist. Now this last one. What's the output for x equals 25 to the nearest hundredth? We're just going to do a little estimation here. Now this goes in relation with an activity we did in class. We can narrow it down a little bit. So I've got my handy calculator with me. If I want the exponent I put on 2 to get 25, well, 25 falls between 16 and 32. That means that my exponent's going to be somewhere between 4 and 5. So now it's just a matter of trying some things. Actually, to make it a little easier to see, I'm going to use my Desmos here. So I know 2 to the 4th is too small. Let's try something a little bigger. Closer. That's getting closer. We're looking for a 25. Okay, that's now too much. So 6 something. That's a little too high. That's a little too low. Okay, so which is closer? So 2.64 was about 0.7, or rather 0.07 below 25. 0.65 is a full 0.1 above. So I'm going to say that 2 to the 4.64 gets me pretty close to 25. Now, it's not exact. That's because we're rounding this. If you want to get exactly 25, you've got to add more decimal points. But we were told here to round to the nearest hundredth. So what exponent got us there? It was about 4.64. Another way you could do that is using our Desmos technology here, is if you just graph y equals 25, and then we look for where these two graphs intersect. Right there it is at about 4.64.